Andrew is an assistant professor here in the Manning College of Information and Computer Sciences at UMass Amherst. His research focuses on the development of artificial intelligence methods to enable scalable and effective personalized learning in education. His research spans Okay, like I said, he's working on personalized learning in education. His research spans areas such as modeling learners, personalization, content generation, and human-in-the-loop AI. Relates very much to a lot of the stuff we're talking about here. Today, he's going to talk to us about GPT-based open-end knowledge tracing. So please welcome Andrew Lynn.
Thank you, James. So first of all, before going into the talk, I apologize that this is not going to be any related to search, unfortunately. Well, hopefully, we can use search in some place in our stuff in the future. But
learning and language.
Learning and language. Okay, yeah. So, but this does have something to do with language, right? So this work is done with my collaborators at Rice, and collaborators in my sense means they do exactly what I tell them to. So in this particular work, I think you can imagine there will be them being replaced by GPT-4, and it won't make a huge difference. Right. So background is, what is knowledge tracing? So James had a hard time, reading those words. I'm pretty sure he hasn't seen them before, right? So knowledge tracing is this typical tool or problem that people are concerned with when we're dealing with student data, right? So usually, let's think about this following setting where you have an intelligent tutoring system, and then a student has an account in that system, and then you're constantly doing learning activities within that system, right? So, but what happens is the system needs to know, okay, like at each particular point in time, what is your current knowledge state? What is your current mastery level of all the knowledge components or the skills, right? So, and where does the system get this information is, of course, from your previous interactions with the system, the previous questions that you have answered in the system, right? So the problem, though, is that, you may think that now you're going to realize, oh, I'm working in a community where most people aren't, well, the standard practice isn't that smart. But you'll see that. So for the last 20, 30 years, what people have been doing is that they've been operating with binary valued correctness answers, right? So a correctness data, which means that if I'm trying to analyze a student's mastery level or knowledge levels from their past behaviors, all the data that I'm looking at is essentially whether they got this problem correct or incorrect. Now, there has been a lot of there are many reasons why you do that, well, 20, 30 years ago, where number one is grading scalability is an issue, right? So you want something that's easily gradable. But these days, thing is, we have so many, open-ended questions, so you don't necessarily have to ask students to select one option from multiple choice options. It's kind of bad, right? So, and the thing is, in these situations, the exact answer that the student writes to a particular open-ended question means much more than just abstracting it into a binary information, which is correct or incorrect. And this is the exact limitation that we're trying to deal with in this work, right? So we're going to just look at open-ended answer. And maybe this is surprising, but people in our community hasn't really done much with this, right? So in this particular work, what we do is that we develop this thing called open-ended knowledge tracing.
I just want to remind people that because of the way the microphone system works in here, we can hear your murmuring. So we're hearing your conversations back there. Okay. Keep it extra limited if you want. Thank you, Andrew.
All right, thanks, James. Yeah, so and here what we do is that we develop this framework by combining typical knowledge tracing models with the language models. And we are going to use the model to analyze, students' knowledge states and see how they reflect the changes in the actual code that students write. Well, here we're grounding our work in this computer science education domain, so please don't ask me to interpret any of the things that I show in my slides, just because I don't actually know much about computer science education. When we started with this work, the goal was to do things with math, right? So what I really wanted to analyze was math open-ended answers, but the largest open-ended data set that we could find happened to be in computer science. So it is what it is. Right, so that's just an overview of our approach. So our approach basically has 3 components. So I'm going to skip through the first 2 because they are more or less standard in the existing knowledge tracing literature. So the first one is called knowledge representation. So what that means is that you need to somehow summarize a student's past activities. And in this case, we just use a bunch of very standard techniques, because in the situation that we're dealing with, we're looking at program questions, which is students need to write a piece of code that implements a particular requirement, right? Write a function that implements this desired thing that you want to implement. So the problem statement is essentially a natural language description of the task. And then what the students write is a piece of code, right? Usually 5 to 10 lines, right? And for both of these, we essentially just use very standard tools. So we just stack all the text embedding vectors for each one of those words, and also for code, we use ASTNN, which is abstract syntax trees, and then we use this tool to embed everything into a vector. And then we input that to the next layer of our model. So the next component is called knowledge estimation. So what this means is that I'm going to try to take a student's past or all the past answers to previous questions, and then turn them into this latent knowledge representation. And the thing is, this has been done in the literature for many, many different years. There are hundreds of people doing this for binary value knowledge tracing. So I'm not going to emphasize that, but basically it's just, I would say it's kind of just an LSTM. It's just a recurrent neural network and very many different variants of it. But basically you're just doing an iterative update at each time step after you observe one particular piece of student code. And that's also standard. The non-standard part is which is the emphasis of this work, is called response generation. So because the previous case where we deal with binary value correctness predictions, then you're just predicting whether the student's getting a question correct or not, then you just need a linear classification head followed by a sigmoid. That's super trivial. But in our case, this is actually quite different because we need to predict the exact code that the students are going to write, right? So what we do is we use a text-to-code generated pipeline. I mean, you can use Codex, but we could not use that because here in our case, we need to actually modify the language model. So you can't just use it. So, I mean, you can't modify Codex, which is why we kind of used our own method. We just took like a GPT-2 and then we pre-trained it on millions of Java code pairs and their corresponding textual descriptions. And so use it as our codex, basically, that we can modify. And the challenge here is that, because the thing is, different students write different piece of code for the same question, right? There are many, many different clusters in students' code and different types of patterns. So we can't ask the model to generate the most likely output because that's the code that some expert is going to write, right? If you just take the text-to-code model, it will try to predict the correct code or a very elegant piece of code. But these are students learning programming. Some of them have no idea how things work. You can see a bunch of really ridiculous implementations in the data sets. So you need to somehow steer this generation in a way such that the generated code reflects the student mastery level on different code concepts. And so this is the key here. And what we do is that, so the challenge, actually the technical problem boils down to how do we use the latent knowledge state for a student to serve as the control in this controllable text generation problem to generate different piece of code that reflects different types of patterns in different ways that you can implement a piece of code that satisfies some requirements in different ways, some with errors, some with no errors. And the particular solution that we have here, I mean, there are so many ways you can do this because you can think of each knowledge state of a student, which is just a vector. You can think of this as the control. You can inject it into in so many ways into a language model. You can use a soft prompt. You can use additive embeddings, which is what we do here. And you can also inject into intermediate layers. But here, as for the first case study, we just use it as an additive embedding in the input space. In other words, what we are dealing with, you can think of this as being, we are using the knowledge state to perturb the input space so that the students have the input to the textual code pipeline, like a perturbed version of the original text that describes the task, and then you generate, and then the output would be, code that has different properties according to each student's current knowledge state. So, and what we found is that, well, a linear combination, learnable linear combination of token embeddings and knowledge state works the best among all the other things that we tried. So, one observation. Another intuition that you can think of this is that, well, since this is controllable text generation, right? You can think of each student working on each problem as a separate task. But then the thing is, if you learn a control, but the thing is, the control here is not learnable, is not observable. You don't know what the control is. So you need to learn what the control is. However, you cannot just let the control space free flow because that's just a huge space. There are so many students writing so many pieces of code. You cannot have a set of parameters representing each one of these situations. So you need to regularize the space. The way we of course, you can use tools such as clustering, all of those things. But the way we are specifically regularizing this knowledge space is by using the continuity in time, which is the student's knowledge states cannot really jump dramatically. From time to time, so for me, like my knowledge here at this particular point in time, is not going to be significantly different than my knowledge state 10 minutes later, right? After I hear about some of your questions. I mean, of course, some questions may be super enlightening, but compared to the history of my life, then it's not going to be a huge jump, right? There's some temporal consistency here, and that consistency is handled by knowledge tracing models in the literature. So, okay, so I'm going to show you some results. So we basically since this is a code generation task, we use Code Blue to model, to measure code similarity. And so there's a nice data set for it, which is fortunate. So we used it so there are two settings. You can predict the student's code for the first submission to every problem. You can also try to predict all the submissions. But the thing is, I think in this particular scenario, modeling students' first submissions makes more sense. It's just because these are programming questions, right? Students write their stuff in the box, and then they press compile, and then they have errors, and then they revise their code. So nobody tries to submit their answers in like one shot. Right? So analyzing all submissions is actually quite tricky because that involves some debugging behavior. So I would say we prioritize on analyzing first submission as one example. The reason why we can't answer, final submission is that after many attempts, almost everybody gets everything correct. So here we try different things, different existing knowledge tracing methods as the knowledge tracing component, and we found that the simpler the better, which means that you just slap like an LSTM onto it. It actually works much better for our purpose than some other fancier algorithms and models that work best, when you're dealing with binary knowledge, binary value states in response prediction. Okay, so there are a bunch of other things. So let's actually skip through these. So I'm just going to give you some sense of what we are doing. So on the left, we have predicted student code, and on the right-hand side, we have some actual student code, and the differences are highlighted in these red boxes. So if you don't know how Code Blue kind of works, so these are some qualitative examples. So the first case, the Code Blue is like 0.8. The second case on the bottom here, the Code Blue is like 0.65. And then if you go to these numerical results, the best result that we have in terms of predicting first submission is about 0.7. So it's somewhere in between these two examples. But generally speaking, what we found is that you can somehow capture some structure and approach in students, capture the variance in student co-submissions, because there are many different factors at play here. You have style, you have insufficient knowledge, you have specific misconceptions. You can analyze many things out there. In terms of detailed performance breakdown, we found some across these different problems. So we've actually found that there's no obvious conclusion. Sometimes more examples and more diverse examples do not really improve code prediction accuracy. But the only thing that we found was that indeed for easier questions where there's probably these are easier programming questions that are less variations in student code, it's easier to predict, but that's kind of just as expected. Okay, so we also use like a case study to try to interpret what the latent state of knowledge state means. Right? So unfortunately, I'm not an expert here, so and we are trying some ideas relating to, say, for infogans, and then trying to interpret this latent state to make them more meaningful. But the short story is that you can visualize these latent knowledge states in this latent space, and then try to see how they correspond to actual student code. And there are examples to make us believe that this does capture some sort of behaviors and patterns and specific errors made by students in their programming code submissions. Okay, so one cool visualization I thought I'd show you is that, so this is the meaning of why we're doing this. So from left to right, so on the left, this is exactly plotted on the same data set, trying to interpret the latent student knowledge states. So on the left-hand side, this is using binary valued student knowledge, student responses as both input and output in the model. And you see everything is kind of like jammed together in a couple of strands. But in the middle, once you use the exact code, transfer it to AST&N and use it as input, but not output, you start to see the space disentangling a little bit. But on the right-hand side, which is what we do, once we use both the actual code as input and at output to predict, then you see that things are further starting to separate. Now we can try to make this latent space more meaningful than before. Okay, when we also tested how well does this thing generalize to previously unseen questions, because that's really what we care about, right? If we don't use the exact content of the program in question and the code, then we can really just deal with existing questions. But now, once we deal with the exact text, we can do it for new questions as well. And we're just predicting what students would write in a previously unassigned question. And we can do somehow okay, I would say. So the code blue dropped by 0.2. But in some of these questions, we can actually do a pretty good job of figuring out, what are the major variants in student code that will. So put it. All right, so so this is what we've done, and there are so many avenues of future work. I do believe that this should be the future, although people in my community may disagree. They may choose to keep working with incorrect information. No control over that. But there are so many things to do. So we're looking at debugging behaviors, right? Like this revisions of code, and using an edit process, which include that on top of for consecutive submissions, and try to take the error messages as feedback as well. And we're also trying to use things that are trying to make the latent space more meaningful by maximizing the mutual information between that and code submissions. Right? So just some examples, and we're happy to discuss if you're interested. All right, thank you.
Andrew has made sure that there's no time questions, but we can take one.
So this is a verification, not a question, but you guys were able to predict the exact variable names too that the student would be writing in their code, or it's just the structure of the code that was matching with?
Oh, good question. So in this particular case, for the programming questions that we're looking at, the variable names aren't necessarily, there's not much wiggle room in them. So we could actually predict that. But I think that's just because, in most of these cases, the names are already predefined. But generally speaking, yes, we do need some sort of standardization, right? When this is more open domain question, type of question, programming questions, yeah.
Follow-up.
Yeah.
Have you ever considered using Java bytecode for comparison rather than just plain code? Because you can write code in different paradigms, but if your logic is similar, your job bytecode should be very similar. But yeah, it should lower the barrier.
Yeah, absolutely. So I think that's a good point. So there are different ways that we can evaluate this. You can also use test cases. I mean, we can also, there are many ways you can, so the thing is, this data set, I mean, at the point that we did, at the time when we did this work, we didn't have access to any of that. And we could also use, for example, like just execution traces, but that is, I would say, slightly harder because in many of these submissions, it's not actually compilable. But you know, there are many of these different things that we should look at, and I agree. Other metrics.
Thank you, Andrew.